everyone, thanks for watching this video. This is a presentation about the work I did 2 years ago when I was a postdoc at Geological Survey of Canada with Dr. Joe Spelfler. The title of this presentation is Joint Transmission and Reflection Traveltime Tomography using the fast sweeping method and the Adjoint-state Technique. Hopefully this is not the longest title you ever seen, so hopefully you will like this better. All I want to say is I did some travel time tomography using transmission and reflection travel time simultaneously. I used the fast sweeping method to calculate the travel time and using the adjoint method to perform the tomography or tomographic inversion. This algorithm combines the advancement of this new method, fast sweeping, and the fast adjoint method, and it shows a very promising result in recovering multi-scale heterogeneous velocity structures. And comparing with the transmission tomographies, these algorithms can recover the velocities down to a depth that is not recoverable by only using first arrival tomography. So I'll come back to discuss to explain the details of these two methods in details in the following slides. But before that, I want to introduce you the backgrounds, why we come up with these algorithms. I was involved in the gas hydrate reservoir characterization project in the permafrost, where the near surface is covered by multi-scale heterogeneous environment, permafrost. By saying multi-scale, I mean the thickness of the permafrost is changing from less than 100 meters to more than 500 meters in a horizontal scale of tens of kilometers. And on top of this long wavelength variations, there are small-scale lakes that are frozen in winter and melt in summer. So this type of near-surface condition is not only observed in permafrost, can also be observed in a hard rock environment or like a mining site. So this type of near-surface condition is not seismic friendly because it significantly damages the seismic image of the deeper target. Therefore, we follow the conventional wisdom but propose to use grid-based econo equation solver such as the fast sweeping method to calculate the travel time, and use the adjoint method to convert the inverse problem to another forward problem, which can again be solved by using the fast sweeping method. We implement this algorithm on a parallel machine. It called a PFAST. It stands for Parallel Fast Sweeping Based Adjoint Seismic Tomography, and hopefully this program will be released as an open source software soon. And I will demonstrate the performance of this program on the synthetic datasets and on the field dataset before I draw some conclusions. So here is our project, located right here in the northwest territory of Canada. This satellite image shows you the near surface distribution of the lakes or water bodies. Many seismic surveys has been conducted in this area, 2D, 3D, and in our study we are interested in this one line 120 because this is more or less in parallel with the axis of the anticline beneath. So the reflections acquired by this line is more or less flat. Although this line was designed to avoid the major lakes, but it still intersects a few lakes at multiple locations. The consequences can be observed in the pre-stack time migrated seismic image. As you can see, marked by the red arrows here, the consequences is either produce no information or it just significantly smearing the energies all the way down to a certain level. There's one reflections I managed to pick, like this one, marked by the dash white lines. This will be the reflectors I use to do the reflection tomography later, and we'll come back to this point later on. The nearest well lock is located here in the northeast side, 2 to 3 kilometers away from the line. Generally, there's 3 intervals are identified. The first layers is the permafrost that we are interested in this project, and then it's the sediment saturated by fluid and sediment saturated by gas hydrate. In general, the velocities in the permafrost is increasing first and then decrease, and this is common in permafrost because the velocity is generally increasing with depth. So does the temperature. So there is a certain level, the temperature is so high that it starts to melt the permafrost and decrease the velocities in the permafrost until its value reduced to the value of the ordinary sediment saturated by fluid. So I'll refer this velocity turning point or refer to velocity turning zones. I use this cartoon from EOS to summarize the problems we have here. Our understanding of the near-surface structure is quite limited, and that severely damage our seismic image of the deeper reservoir. So the question is, can we undo this impact? One of the ways is to characterize the near-surface velocity and use that velocity model to correct the seismic image of the deeper target. Currently, there are many techniques available to build a near-surface velocity model. For example, refraction method, which represent the velocity of the Earth as a constant layered model, and assume all the first arrivals is the refractions along the interface. So by only changing the thickness of each layer to minimize the differences between the calculated first arrival and the observed first arrival. So this method works very well in many cases as long as the geology is more or less layered and the velocity within each layer is more or less constant. But in our case, we don't have a layered permafrost, and the velocities is not constant. It's multi-scale heterogeneous. So therefore, the alternative is just to abandon this assumptions of refraction and the constant velocity layers, and just use the first arrivals to update the velocities as a function of space, pixels by pixel, as you can see in this picture. This is also from a permafrost environment, and the picture shows that the turning rate tomography, the so-called turning rate tomography, works in this environment. And actually, the turning rate tomography is just a classic first arrival seismic tomographies. The turning rays, if you remember the velocity turning zones in the well logs, as I show you in the last slides, the turning rays used in this method actually will turn above the velocity turning zones. So therefore, the turning rate tomography only recover a very shallow part of the permafrost, and the problem remains. We don't know the lower part of the permafrost. Therefore, we propose to include reflection arrivals in the framework of travel time tomography. To do travel time tomography, we usually perform two steps. The first step is to calculate the travel time, and the second step is to do the tomography to update the velocity iteratively till the velocity model converge. Generally, ray tracing can be used to calculate the travel time for both transmission and reflection arrivals. However, in our case, it can be problematic. For example, a point source is located in a smoothly varying heterogeneous model. The angle distance between the adjacent ray path at the source location is identical, but that uniform fan structure is not preserved when you move away from the point source because the Econo equation is nonlinear. So a few problems arises. For example, multipassing. If you have a receivers at this location, you can't distinguish the late transmission arrivals from the reflection arrivals. The other problem is the shadow zones. The velocity structure will make most of the rays avoid zones like this, so it forms a shadow zones. If you have a receivers on top of the shadow zones, it's very challenging to calculate the ray trace from the point source and arrives at this point. So the alternative is to use a grid-based method. It becomes more and more popular these days. The basic idea is to just use a finite difference method or a finite element method to discretize the Econo equation and solve the travel time as a function of space. Currently, there are two competing techniques, fast marching and the fast sweeping method. The fast marching method goes like this. If this is the digitized model, velocity model, the fast marching method will first define the point that has the correct travel times as alive points, and the points that doesn't have the write travel times as the far points. The boundaries between these two group points are called the narrow band. The fast marching method will use the information from the alive points to calculate the possible arrival times for each grid point within the narrow band, and only pick the points that has the minimum travel time, for example this one, and update that points only. So the narrow band get updated, and it will repeat these steps in the following step till the full velocity model get covered. So as you can see, there is a sorting algorithms because you have to find out which point has the minimum travel time, and also it has to be performed in a sequential manner. Therefore, it's very difficult to parallelize a faster marching method on current parallel machines. The faster sweeping method, on the other hand, doesn't have a narrow band concept. It just simply sweep through the model multiple times till the travel time field converge. As you can see, for example, in a 1D model like this, the point source is located in the middle, so the arrival time for that point is 0. The rest of the point has no information, so they are assigned infinity. Faster sweeping method starts from one point and use its neighboring point to update the velocities at this point, and move along one directions. And for example, start from this point because its neighboring point has no new information, so this point remains the same till it reaches this point. It will be updated by the point source, and those points will also be updated by the points or its neighboring points one by one. And after that, the sweeping method sweep backward to update those points. So for a 1D model, it takes 2 sweeps to calculate the travel time, and for 2D model, it takes 4 sweeps, and for a 3D model, it takes about 8 sweeps. So and each sweep is independent on each other, so they can perform simultaneously. So if your CPU has 4 cores, you can just perform the sweeping simultaneously, and you achieve a 4 times speed up right away here. So therefore, we pick the faster sweeping method as our forward model engine to calculate the travel time. As you can see, this is an example calculated from the faster sweeping method. The model looks like this. The velocity increases from top to the bottom, in each layer dipping along in different directions. It's 100 meter cube. The grid interval is about 1 meter. So we have, in this model, we have 10 to the power of 6, about 1 million grid points. The source is located in the upper corner. Using a single core without parallelization, it takes 7 seconds to complete the travel time calculations. So this is the plot the travel time field as a function of space, and the plot A just shows you the isosurface of the travel time field. It mimics the wave propagating away from the points here. To calculate the reflection arrivals, we need to add one more step. The first step again is just to propagate the point source, propagate the wavefront from the point source all the way to the first reflective interface, and then you record the arrival times along the reflective interface and reinitiate the calculation again. According to Huygens' principle, the receivers on the surface, the travel time for receivers on the surface is the travel time for the point, and here equals to the reflections from the point source down to first the reflector and back to the near surface. If you want to calculate the reflections from the second layer, you just repeat that, propagate the wavefront to the second layer, and then up propagate again. If you want to calculate the multiple reflection, you can do that as well. You just track that up, down multiple times. It's up to you. So we have a very efficient travel time calculator. The next step is just to perform the tomography. A classic tomography formulates the problem as a sequence of linear problems. Like A is your operator matrix, operated on your model, vector M equals to the data vector D. And then there's many techniques to solve a linear problems like that till your model converged. Adjoint method that goes in a different way. He formulated the problem as optimization problem under the constraint of partial differentiation equation. the optimization, as you can see in this formula, E is the error or the energy. It defines as the differences between the calculated travel time and the observed travel time. The goal is to minimize the error subject to a constraint of the Econo equation. This is a general expression of the Econo equation. T is the travel time as a function of space x, c is the propagation speed, omega is your modeling area, and gamma is your boundary condition. So if it's a point source, then gamma is just a point. If it's for reflection calculation, then gamma is your reflective interface. So the inverse, the adjoint method, just to formulate, the goal is to minimize the error subject to the Econo equations. A usual way to minimize the objective function subject to equal constraint, the usual way is just to use a Lagrangian multiplier lambda times the left hand side of the constraint minus the right hand side of the constraint, and then add this new term back to the objective function to form a new objective function without constraint. And then the next step is just to find out the variation of E with respect to the variation of C. But we don't want to explicitly evaluate variation of error with respect to the variation of speed, because that's computational intensive. Keep that in mind, and after some geeky algebra, we end up with a new partial differentiation equation, usually called adjoint equation. It's an equation about the Lagrangian multiplier lambda. Lambda is a function of space. So if lambda satisfies the equation, this partial differentiation equation in the model, and also this condition at the boundary where you have receivers, then the variation of E can be directly calculated from lambda. You can also choose the variation of C, the speed, equals to negative lambda over c cubed. It's very easy to verify. The variation of speed will reduce the error. You just substitute this expression back to this integral. You will realize that the delta E is guaranteed to be non-negative. So that means this type of velocity perturbation will decrease the errors. And the next step is just to update your velocity model. Cn is your current velocity, alpha n is the step size, and the delta m is the perturbation of the model. If you're using steeped descent method, delta m equals to delta c. If you're using conjugate gradient method or any other method, delta m can be calculated from delta c. In our case, we like the quasi-Newton method, limited memory BFGS method, because it's the convergence rate is much faster than the conjugate gradient method. So here is the example using the adjoint method techniques. The velocities on the top is quite simple. The value of the velocity is increasing from the surface all the way down linearly. There's one anomaly in the center of the model. Source receiver is deployed along the surface, and there's a reflector at the bottom. Just to see how well the adjoint method can recover the anomalies, we just used initial velocity, the background velocity, as our initial velocity. So these are three examples after the first iteration. It shows the velocity perturbation using transmission time only, velocity perturbation using reflection time only, and the velocity perturbation using adjoint, using both arrivals. So as you can see, the transmission tomographies has very good vertical resolution but not horizontal, and the reflection tomography has very good horizontal resolution but not vertical resolution, and the combination of them provides you the best information about the anomalies. And this is only the first iterations. After multiple iterations, it just recovers the anomalies very well. So the last step is to implement this this algorithm on a parallel machine. Currently, there are two parallel programming models based on the memory architecture: shared memory model or distributed memory model. The left upper corner just shows you an example of the shared memory machine. It can hold up to 700 cores and all the cores can globally access 6 terabyte memories. So the advantage of this shared memory machine is the communication between the cores is minimized. But there's a big disadvantage of a machine like this. The scalability is quite low, so if you want to increase the number of cores, you have to either wait till the technology becomes economic, or you just pay a chunk of money to get a machine on your own. On the other hand, the distributed memory has a very high scalability. It's simply just to connect the multiple CPUs using a network, so you can combine as many as possible like this. The number one fastest computers in the world currently is from Japan. It's called K computer. It's connected 80,000 computers together. If you have more computers, you just add them on. The other advantage of this distributed memory model is you can even make your own clusters using off-the-shelf commodities here, as long as you have an adapter and you have multiple computers. You just connect them, and you can form. Then you have a cluster. Even myself, I make myself an 18-core cluster, actually 3 nodes, using a Helmer drawer from IKEA. So people call that Helmer cluster. This is the network adapters, and they connected the 3 nodes with the master computers, and master computer is quite old, 5 years old. So it's just to distribute the tasks to each node. And each node has 6 cores, so now I have 18 cores. The 3 drawers is currently empty, but you can add more nodes to that to get a 36 cores clusters as maximum. So we decided to implement this algorithm on a distributed memory system using message passing interface to assist the communication between CPUs. So hopefully this program will be published by Computer Science soon. The picture just shows you the workflow of these programs. The first step is to distribute the multiple shots to multiple CPUs as evenly as possible. And then the second step is to calculate the travel time. The third step is to calculate the velocity perturbation. And usually the raw velocity perturbation has high frequency noise, so you use some a low pass filter to regularize your velocity perturbation. And the fourth step is to use that velocity perturbation to update your model. You can use HS conjugate gradient or nonlinear conjugate gradient or limited memory BFGS method. It's up to the user to decide. And then the fifth step is to decide the step size. There's a condition so-called a strong wolf condition. That condition just to guarantee that if you choose a step size like this, you are guaranteed to end up in the bottom of the valley. And then one of the CPUs will check if the velocity model converged, and the rest of the CPUs will start updating the velocity model of their own version. If the processors found the velocity model converged, it will terminate the program. Otherwise, it will let the rest of the CPUs update their own version and then repeat step 2 and step 5 iteratively till the velocity model converged. So as you can see, the CPU time is significantly decreased when you increase the number of cores. We can also look at this using speed up. Speed up is defined as the ratio of the computation time using 1 core over computation time using multiple cores. Ideally, if you have 16 cores, you should achieve 16 times speed up, but usually it's not. This ideal model usually is not quite possible, but our program achieves a close to linear speed up. And those platforms, as you can see here, is when the number of shots cannot be evenly distributed among the number of cores. So it works. Its scalability is quite well on multiple machines. Then we apply that to a simple 2D model. It's synthetic data case. The model is quite simple, 2 layers with irregular topography. The velocity in the first layer increased from the near surface all the way down to a certain level. After this level, the velocity becomes constant, and there are 2 anomalies in each layer, positive anomaly in the top layer and negative anomaly in the bottom layers. There's reflectors at the bottom, and the source receivers are along the surface. So here's the result: transmission tomography only, reflection tomography only, and the joint tomography. As you can see here, transmission tomography only recover the near surface structures, because after this level there's no turning rays coming up to the receivers. Well, there are energy coming from the second layer coming to the near surface receivers, but they're not first arrivals. The reflection tomography recovers both, but it has a slightly vertical elongations, particularly for the lower anomalies. It even smears across the boundaries here to the first layer. The best images is provided by the joint tomography in terms of the shape, and also they are constrained. Like this lower anomaly, it's constrained within its own layer. So the other thing I want to point out is the reflection tomography. In the reflection tomography, we use a very large offset, and because of a large offset like this, it tells the programs that I don't observe a large anomalies on my way here, so don't allow this anomalies to smearing all the way up to the near surface. But if you don't have a large offset reflections, because of the vertical propagation direction of reflections, the reflection tomography tends to smear the energies along the vertical direction, and that you will observe that in the real data case. The field data is from the permafrost region. Again, it's a satellite image, shows the seismic survey lines. There are in total 386 shots, and about 77,000 first arrivals were picked, verified, and make sure they are good quality. And then I use this reflections and then pick the reflections for each shot gather corresponding to that reflector, and they are about less than 15,000 reflected arrivals were picked, and most of them are near offset, as you can see in this shot gather example. As you move away from the source, the offset, when the offset increase, the signal to noise ratio is significantly decreased. So it's very difficult to tell, to follow the trend of the reflection, the curve of the reflection. So therefore, our philosophy is that we rather have less but good data instead of more but unreliable data. So here's the result. The first picture shows you the transmission tomography only, and the bottom shows you the joint tomography. In general, the transmission tomography controls the near surface structures, and the reflection tomographies controls the deeper velocity informations. Specifically, there are 4 regions corresponding to the 4 lake areas. The low velocity corresponding to the lakes that are intersected by the lines, and when you include the reflection tomographies, those near surface structures is just enhanced when you're including the reflection tomographies. And there's a level, I call that peak velocity profile. It's just corresponding to the velocity turning zones we observed in the well logs, and this picture does confirm that there is a long wavelength variation within the permafrost, and after this layer there are some low velocity zones. Particularly for these lakes, the transmission tomography only recover a shallow part, but in reality it is not that small lake. It's actually a quite deep lake, and even deeper than the reflectors here, and that actually explains why we have a significant seismic smearings in the pre-stack seismic data. On the right corner is just there's no ray coverage, so the velocity maintains its initial value. So it gives you a basic idea what is the initial velocity looks like. None of those structures are present in the initial velocity. They are covered from the data. So I can join my conclusions here. We implemented a parallel fast sweeping based adjoint seismic travel time tomography using transmission and reflection travel time simultaneously. We applied that to a 2D synthetic data, and it recovers both near surface anomaly and also the deep anomalies. We apply that to a field data, and it recovers the multi-scale heterogeneous velocity structures within the permafrost. And hopefully that information will help us to improve the seismic image of the deeper target. Oh, and if you want to do a moment tensor inversion these days, velocity information about the near surface can also improve your moment tensor inversions for a reservoir beneath it. Finally, I'd like to thank BP Canada and Chevron Canada who provide our the data to us. And also I want to mention ANSERC Visiting Fellowship Program. Because of that, I can work at Geological Survey of Canada for about a year. Finally, I'll leave you a picture from permafrost. Thank you very much.